So we know what flow past flat plates looks like, but now we want to try to actually do the thing that we're kind of here for, which is to understand how convection occurs inside of systems that can be modeled as being flat plates. And to remind you what that looks like, the whole idea is supposed to be that we have kind of this uniform background flow generated by some object or whatever that has a speed of u infinity. So we have this flow kind of uniformly coming in at speed u infinity. We also have that this liquid, this thing that's being flowed over this flat plate, has an asymptotic ambient temperature of T infinity. All right, so far away from the plate, the temperature of the liquid is T infinity. And this liquid has some material properties, most of which are old friends, right? We know the specific heat capacity, we know the thermal conductivity, we know the density, and then we were recently introduced to the dynamic viscosity in the last lecture. So these are the four kind of material properties or parameters that describe the liquid that's flowing over this thing, or the fluid, whatever. This fluid flows over a flat plate with length L and width W, and the plate has some uniform temperature Ts, right? So the surface temperature of this plate, which we're going to assume is like very, very thin, is just Ts. And so the question that we want to ask ourselves is, what is the H, right? Because knowing what the H is allows us to understand what the heat transfer is in terms of the heat transfer rates and the heat fluxes, what those things are between this plate and the surrounding liquid. All right, so how do we write that down? Well, we have to be careful because there are actually two different ways that we could define an H. All right, we could create what's called a local H, which is the kind of old standard definition that we created for the H, which is just that Hx is equal to, Q double prime. So the heat flux divided by the difference in temperatures, right? Which is, in this case, just Ts minus T infinity, or T infinity minus Ts, depending on where you believe the heat fluxes are going. And so the whole point is supposed to be that this local H is a function of where we are on the plate, right? Because hypothetically speaking, we know that the flow that's happening through this flat plate changes as we go further and further along, right? So if we define this coordinate system X, we would find that as we go further and further along down this plate, the H could change because the characteristics of the flow around the plate change. If that's the case, right, then calculating the net heat transfer that happens through the system becomes very, very complex because we have to find what each of these individual heat fluxes are and then integrate all of them to get a net heat transfer rate. Nevertheless, this is still perfectly valid, and it helps us understand how the local heat transfer coefficient, right, how effective heat transfer is in one location of the plate versus the other. So it's still super useful. The other thing that we can do is we can define what's usually referred to as an average H. And this is just the proportionality between the Q, right, the net heat transfer rate that's happening from the plate out to the surface, divided by the surface area of the plate, which is the surface area over which the heat transfer takes place, right, times the delta T. And so in this case, the idea is that we get rid of the integration, right? This H is just the effective ratio between these two things. So if we can find what this H is, then we can directly connect, we can use a single value to connect the net heat transfer rate down to the temperature difference and then, the surface area as well, right? So this one tends to be a bit more practical if we're trying to study like heat transfer in engineering systems, because often we don't care about the local heat transfer rate. Often we just care about how much heat is moving over time from one object to another. So this is the one that we're going to be working with almost all the time. But notice that I can define two of them, okay? And there's no way that we're going to be able to get this number other than via experiment, okay? So whatever the H is, which we're just going to work with the average H for now, whatever this H is, there is no fundamental equation that tells me what it's going to be, right? It'll change depending on what the systems are. It'll change depending on what the material conditions are, and it can only ever be derived by a series of complicated experiments. So we're not here to talk about physics, really. We're here to talk about, or at least theoretical physics. We're here to talk about how we can try to create an expression for H as a function of all of the other parameters that are in the system that will allow us to relate these things simply, right? That will somehow create a simple set of experiments that we can do to actually figure out what's going on, in the same way that we try to frame the notion of understanding turbulence inside of these systems as being just a function of one dimensionless parameter rather than four-dimensional parameters. Okay? So how do we do that, right? Well, like I mentioned, right, this H is a function of a bunch of stuff. For the moment, I'm going to assume that this H is only a function of temperature differences and not the individual temperatures. This is a very bad approximation, but for now, let's work with this. Okay, so we only get the temperature differences showing up here, and then all of these nice material properties. I suppose I could add the W over here. So, yep. And you can imagine that there's a bunch of other stuff that maybe we're not considering inside of our drawing of this system that could affect what this H is. But rather than do an experiment where we control for every single thing here, like each individual thing, what we really want to do is try to see if we can't come up with a dimensionless relationship, right? Convert this H into something that doesn't have dimensions so that we can relate it to other groupings of these parameters that don't have dimensions either. So how do we do it? Well, the first thing that we want to try to do is to avoid using the H at all. Okay? Rather than using the H, we want to create some kind of meaningful dimensionless number that is a function of H. And then we want to relate that dimensionless number to the other dimensionless numbers that we can construct in this system. Okay? And although it is relatively arbitrary, right, there's a couple of different ways that you could create a dimensionless number out of, H and some other stuff. For flow past flat plates and for average H's, mind you, usually what we do is we just say that we want to create the following dimensionless parameter. And if we were dealing, by the way, with local heat transfer, so if we had heat transfer that was happening, if we wanted to model the H at a specific point, then we could just do Hx times x divided by k. Once again, there isn't a specific reason why we want to choose this specific grouping other than the fact that this is just kind of the convention over which the experiments have been done. And it's particularly simple. I mean, the only things that show up are the length of the plate, which matters, and the thermal conductivity. And by the way, I should mention the thermal conductivity that we're considering is the thermal conductivity of the liquid, okay? It doesn't matter what the thermal conductivity of the plate is, at least not for now, because of the fact that the plate is infinitely thin. So any conductive resistance, the place where that factors in, wouldn't matter. So this K is the K of the liquid. And so either of these expressions is usually referred to, in terms of its dimensionless form, as a Nusselt number, which is referred to with the letters NU. Okay? And so now what we want to do is, rather than finding an H, we want to find a Nusselt number, and then once we find the Nusselt number, we can use the L and the K to get the H's back, or the X and the K to get that H back. So what is the Nusselt number a function of? Well, we already know one dimensionless parameter that we can build out of this, because all of the terms that showed up previously show up right here. And so once again, if we're working with the average, heat transfer coefficient, then we can construct a Reynolds number out of the dynamic viscosity, the mass density, the background flow speed, and the length of the plate, if we want the average, right? and I put this subscript L on the Reynolds number, the old familiar friend that we had seen before in our previous lecture, just to indicate that the length scale that we're using for that Reynolds number calculation is the L. Okay? If we were doing this locally, if we wanted to calculate the Nusselt number at a specific location, then we would use a Reynolds number that is a function of what the x value of that location is. In the same way that we use an x value for calculating the local heat transfer coefficient out of the Nusselt number in the expression we wrote before. So that is one dimensionless parameter. Do we have another? The answer is yes, we do. It's not super obvious, and this one's new, right? And the interesting thing about this new one is that it is entirely a function of the material properties of the liquid. Okay, so how does that work? Well, for the moment, we have these four parameters. We already use the density and we already use the mu. So if we want to get something new out of this, something that isn't just like the Reynolds number back again, we should use one of these expressions, right? We should use either the specific heat capacity or the thermal conductivity. And we might as well just use the specific heat capacity because why not? So if we do that, let me see if I can give myself some space. What are the units of Cp? This has units of joules per kilogram degree Celsius or Kelvin, doesn't matter. And we need to find some combination of things that will take this expression and create something that does not have units. Now be aware, right, this joule can be deconstructed. You won't have to, you'll see why in a second. But hypothetically speaking, I could break this joule into kilograms and meters and seconds. But we won't have to because of how we've defined the things that we're going to divide and multiply over here to simplify. Right? So what's the first thing that we should try to do? Well, we want to get rid of the joules, but we also want to get rid of the temperature difference. Okay, so we could just multiply by this temperature difference, but remember that we want to try to see if we can do it with only material properties of the liquid. So what can we do? Is there something else that has like a degree Celsius or degree Celsius difference in the units? And the answer is yes, RK. As a refresher, this has units of watts per meter degree Celsius. All right, and this watt can really be deconstructed into joules per meter second degree Celsius, right? So we broke up the watts into joules per second and then off we go. And so you can see, right, that if I divide by K, I now get rid of that joule per Celsius that was annoying me. And what I'm left with is something that has units of meter second per kilogram. All right? This has units of meter Celsius per kilogram. But we already figured out that this has units of kilogram per meter second. So all we have to do is just multiply by the mu, by that dynamic viscosity, in order to be able to fully cancel out the units. And so what we're left with now is this quantity, Cp times mu over K, which is usually referred to as a Prandtl number, right? And this Prandtl number is the second and last dimensionless number that we can find out of the combination of parameters here. It doesn't depend on the properties of the plate, so there isn't any variation depending on whether or not we want to use the local heat transfer coefficient or the average heat transfer coefficient. The Prandtl number is just as much a material property as Cp, K, and mu are, right? It just doesn't have any units. So any tables where you might see the values of Cp and K and mu listed are tables where you would expect to see the Prandtl number listed too. All right? Now, this all looks pretty nice. All we have to do is that for a given system, right, for a given set of circumstances, we have to find an equation or a set of equations that will tell us what the Nusselt number is as a function of the Reynolds and the Prandtl number. And those equations, right, those empirical relationships that we find are going to be a function of two things. One, whether or not we're looking for a local heat transfer coefficient or an average one, but they're also going to depend on whether or not the flow transitions to turbulence anywhere on the plate, whether or not this REX ever trips past 5 times 10 to the 5, as we talked about in the previous lecture. And so we'll find that there isn't just one equation that we can use to figure this out. That equation would be way too complex. We actually have to create a set of equations and then apply them to this problem-solving process, to this idea to find a Nusselt number based on the characteristics of the flow and based on whether or not the flow becomes turbulent over this flat plate. Okay? And so we will now talk about how to actually do that, the workflow of doing that in the next lecture.